Hello and welcome to this elementary statistics tutorial on the one-sample t-test. In this lesson, you'll practice evaluating statistical significance using the t-test and using the t-statistic to calculate confidence intervals. Recall that the one-sample t-test is a test of a sample taken from a population with unknown standard deviation. The following information must be known to calculate the t-score. The sample mean, x, the standard deviation for the sample, denoted s, the sample size, denoted n, and that the population is normally distributed. For our example, imagine that you want to determine whether zebras living in one region of a country, region A, weigh a different amount than zebras living in another region of a country, region B, due to the greater availability of low-calorie foods and the poorer availability of high-calorie foods. Most studies have been performed on zebras from region A, and their weights are known to be normally distributed with a mean of 500 pounds. You take a sample of 10 zebras living in region B and find that the mean of the sample is 507 pounds with a standard deviation of 0.6 pounds. And you want to know whether the means of the two groups of zebras differ at a 95% confidence level. In order to calculate a t-test for this hypothesis test, we have to know the sample mean, which is 507 pounds according to the problem statement, and its standard deviation, s, which is equal to 0.6 pounds according to the problem statement. We know our sample size, n, is equal to 10, and that the population is normally distributed according to the problem statement. Next, we formulate hypotheses. In this case, the null hypothesis is that region B zebras weigh the same amount as region A zebras. So, H naught is that mu B is equal to mu A. The alternative or research hypothesis is the opposite of the null hypothesis. This is that region B zebras have a different average weight than region A zebras, or H sub A is mu B is not equal to mu A. Notice that we're not predicting a direction of difference here. We're just looking at whether the two means are different. Next, we calculate the test statistic. Recall that t is equal to the difference between the sample mean and the population mean divided by the standard deviation of the sample divided by the square root of n, the sample size. In this case, that is equal to the difference between 507 and 500 divided by 0.6 divided by the square root of 10, the sample size, which gives a test statistic t equal to 3.7. Knowing that the test statistic is 3.7, we now need to look up the cumulative probability associated with statistic in a t-table appropriate to the degrees of freedom equal to n minus 1, the sample size minus 1, which is 10 minus 1, or 9 in this case. This is a two-tailed test, so we're looking for a cumulative probability associated with an alpha level of 0.025 because our confidence level of interest is 95% and we're splitting the tail probability between both tails of the distribution. So let's first determine t for a 95% confidence limit. Because this is a two-tailed test, or one in which no directionality is indicated, we're looking for a t-value associated with the cumulative probability of 97.5%. And so the tail probability is 0.025%. In the t-table shown, you see that the rows are associated with a different degree of freedom each. In this case, we're looking at df equal to 9, and the columns give a different tail probability. We know degrees of freedom, and we know tail probability. So we're able to find out that the t-score associated with a tail probability of 0.025% for 9 degrees of freedom is equal to 2.62. Since we know that the critical t-value is 2.62, we also know that this value is less than 3.7, our t-value. So we've reached a 95% confidence level. Let's determine the confidence level by finding the cumulative probability associated with t is equal to 3.7. Start at the row level because we know degrees of freedom but not the tail probability associated with our t-score. Walk along the row until we reach something close to our t-score. The closest value in the t-table is 3.69. Now look up the column and find that the tail probability is 0.0025%. And the confidence level associated with that is 99.5%. So we know that the two values are different with a 99.5% confidence. in order to calculate the 95% confidence interval, remember that the confidence interval is two-tailed. There is an alpha divided by 2, or statistical significance divided by 2, probability above or below each of the upper and lower confidence limits. The confidence interval is calculated according to the formula. The A, B, or the lower and upper confidence level, are equal to x, the sample mean, plus or minus the t-score associated with alpha over 2 and 9 degrees of freedom, multiplied by the standard deviation divided by the square root of the sample size. We know the values that plug into this equation. X, the sample mean, is equal to 507. S, the standard deviation, is equal to 0.6. N is equal to 10. And the t associated with an alpha value divided by 2 we found earlier is equal to 2.62. We now plug these values into the confidence interval equation to find that the 95% confidence interval on the mean for this sample is 506.5 to 507.5. It is important that you understand how to perform these t-tests and to be able to calculate t-scores, confidence levels, and evaluate statistical significance. This concludes our video, but if you're not completely sure why we did what we did or how we did this,